This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here today with Stefanie Strathdee, who is a distinguished professor at UCSD School of Medicine, also the author of a book, The Perfect Predator: Scientists Race to Save Her Husband from a Deadly Superbug. Stefanie, this book, it's in some sense it's a personal history, and it's a case history, but it's also I think an exploration of kind of how medicine works, how science works. It's an exploration of um, this kind of, I guess, new or rediscovered area of phage therapy. Not phage research, because that's something that I think has been ongoing and very active over the last couple of decades. But the reemergence of therapeutic applications of this phage research. And you talk about how your life was sort of split between being a scientist and a patient's wife. So one of the things I want to talk about is, right, so sort of, why is it that it took a patient or a patient's wife to kind of move the needle on this research? And, isn't it lucky for your husband that he was married to an infectious disease epidemiologist as opposed to some random layperson? So welcome, Stefanie. Lots to talk about.
Thanks very much.
So maybe we can just kind of get started by talking about the superbug phenomenon, right? So your husband was afflicted with this thing that some people called the worst bacteria on the planet, right? This superbug, the Iraqibacter. Um, and this is just one of many kind of superbugs that have emerged that are antibiotic resistant. So how pervasive is this problem? I mean, you talk about sort of a impending Armageddon when none of the antibiotics are going to work against even some of the more routine bacteria. How is this a problem that is kind of becoming increasingly worrisome? I mean, is this kind of like global warming? Do we need to really become much more aware of this problem than I guess we are at the surface?
All of the above. So basically, a superbug is a lay term for a multi-drug resistant bacterial infection. And in my husband's case, his organism was Acinetobacter baumannii. It has this unfortunate nickname of Iraqibacter because so many veterans had come back from the Middle East with this organism in the early 2000s. And unfortunately, poor infection control populated this organism in all the regional hospitals that these patients were sent to in Western Europe and in America. So it's a nasty one. Certainly, tuberculosis is a bigger killer that kills almost 2 million people per year. But Acinetobacter baumannii is considered to be a critical bacterial pathogen by the World Health Organization and the U.S. CDC. And it's because has a very high mortality rate, and it's usually acquired in hospitals for the reasons that I just explained. So but it's, as you mentioned, just one of many different multi-drug resistant bacterial infections that are a problem to human and animal health and planetary health in recent years. So, and it is a problem that's getting worse. In fact, one of the issues that I raise in the book is that the lack of global surveillance of antimicrobial resistance has led us to really underestimate the scope of the problem. So, just to give an example, it was estimated through kind of back of the envelope calculations. In 2016, a report came out from the UK that there was probably 700,000 people that died from a superbug infection every year, and that was going to increase to about 10 million per year by 2050. That's one person every 3 seconds. Well, if that didn't sound bad enough, the Global Burden of Disease program out of the University of Washington published a paper in The Lancet earlier this year, 2022, that found that in 2019, it was actually 1.2 million people that died directly attributable to a superbug infection globally, but almost 5 million died with a superbug infection. So where it was indirectly associated to the death. So that's much higher than HIV, malaria, It's a bigger number than anybody had anticipated, and certainly it's a wake up call that this is a silent pandemic. It's already here. It didn't burst onto the scene like COVID did. It doesn't seem to cause the alarm in the lay community, but it certainly does in the medical field because people are presenting now with bacterial infections that used to be treatable and are no longer treatable anymore because we have run out of successful antibiotics. And unfortunately, the COVID pandemic has made the situation worse. The CDC reported earlier this year that there's been a 15% increase in hospital acquired infections that are multi drug resistant as a result of COVID, both direct and indirect, because people are getting bacterial infections. If they survive due to COVID, they have a weakened immune system, and often there's a secondary bacterial infection. But also, just the fear in the medical profession that COVID could cause those secondary bacterial infections leads to indiscriminate use of antibiotics when they may not be indicated. So that just gives you a sense of how big the problem is, and we really still don't have very good numbers.
So is the problem primarily caused by the evolutionary response to the antibiotics themselves, or is there something about kind of the hospital environment that creates sort of a, you know, optimal environment for, evolutionary acceleration, right? I mean, this presumably this Iraqi was a relatively benign bacteria at some point. I mean, we don't see, I mean, presumably there aren't like hundreds of thousands of people in Iraq or in Egypt, dying of this bacteria on a daily basis. It's hospital borne. Do you think that, I mean, is there something about the hospital environment? Do we need to rethink how kind of hospitals are organized? I was thinking, if instead of having everybody flow into a central location to get treatment for different ailments, if they were dispersed, presumably this kind of evolutionary trajectory would be slowed down somewhat, right?
Well, I guess the first thing I would say is that, multi-drug resistance occurs because there's selection for it. So, survival of the fittest, if you're exposing a bacteria to an antibiotic or a phage, then it's going to kill some bacteria, but the bacteria that survive are resistant and those are selected for. So, and that's like a natural process that's occurring. It's unfortunately, it's when, antibiotics are misused or overused, and both of those things are happening, that we see that there is, the spread of antimicrobial resistance through, gene transfer
Mhm.
and plasmids, which are circular discs of DNA that can carry multiple multi-drug resistance genes. And I guess, certainly there could be improvements in the medical profession, but your listeners are probably unaware, because certainly I was not aware of this at the time when my husband fell ill, that the majority of antibiotics that are used in the US and in many other countries are actually in agriculture and in
Mhm.
farming. So about 70% of antibiotics in the US are actually used in agriculture and in farming to make animals grow fatter faster. It's our addiction to meat. And so some of these cases, it's actually medically important antibiotics that are being used in farming and
Mhm.
agriculture, like spraying streptomycin on citrus trees, when that's been shown not even to work. But there's a huge agribusiness lobby that plays a role here. And unfortunately, some of our own government agencies, like the EPA, have really bowed to some of these pressures. And so there's a big problem here, and most people are unaware of that.
So, I mean, presumably antibiotic resistance is something that would, happen no matter what. It's just a question of the speed with which it happens, right? I mean, you said kind of there's irresponsible and indiscriminate use of antibiotics, but presumably even if antibiotics were used very, very selectively, you know, there would be an evolutionary response, right, by the bacteria, right?
Oh, absolutely. I mean, what we're doing is we're messing with evolution. And so it's also globalization and travel. and mixing between animals, people, and the environment. So we think about antimicrobial resistance and how to deal with it through a conceptual framework called One Health, which is really, this interplay between animals, the environment, and people. And so we need a multi-pronged effort to deal with this. Certainly, we need to improve the antibiotic pipeline. And there's the Pasteur Act is actually before Congress to do that. But myself and others reviewed the language, and I said, it isn't just new antibiotics that we need, new drugs. We need new antimicrobials. And that's broadening the term to consider things like phage and lysins, which are proteins that are derived from phage, and other types of treatments as well. So, I obviously fell into this area through, my personal experience with my husband, and I have to admit that I was really blindsided. Even as an epidemiologist who specializes in infectious diseases, I've been focused my career on HIV and related infections. So, um, Acinetobacter baumannii was an organism that I used to plate on my Petri dishes when I did my rusty old degree in microbiology in the 1980s. And it was considered to be a really wimpy bacterium. All we needed was a lab coat and gloves. But that bacterium in particular has gotten really clever at stealing antimicrobial resistance genes from other bacteria and from the environment. And it has sticky kinds of fingers, if you will, and it can stick to hospital linens, even body lice. So it's really great at moving in when heavy duty antibiotics have been used to wipe out the friendly bacteria in the microbiome. This organism moves in and takes over that space. And so it's been a real formidable foe, and it has a very high case fatality rate.
Mhm. Well, so what's the state of the art in kind of research around antibiotics? I think you mentioned in the book that most pharmaceutical companies have more or less given up on, developing next generation of antibiotics. I mean, that's kind of disheartening. Is that just because there's been too many research dead ends? I mean, we've kind of explored all of the the possible antibiotic kind of agents out there. I mean, why? What accounts for the? I mean, when you look at how much money pharmaceutical companies will invest for the remediation of relatively rare diseases. I mean, these are huge problems. One would think that there would be a lot of money to be made here. Why have the drug companies kind of given up on next gen antibiotics?
Yeah, well, it's true. There's only a couple of big pharmas that are working in antibiotic discovery right now, and it's multi-layered problem. With both push and pull incentives that are an issue. First, though, is that multi-drug resistance, the speed at which it's emerging, because we've mostly been using riffs on previous antibiotics. Not we haven't and had a new class, a real true new class of antibiotics for decades. So if there is a new class coming on the scene, and there's some promising treatments that are being developed, but they take 10 to 15 years to develop on average, $1 billion or more. So it's a considerable price tag. And then the amount of money that is charged for antibiotics is a lot lower than it is for, say, a cancer therapeutic. And then you have the WHO and the UN saying, well, any new antibiotic coming on the scene is going to have to be saved for last resort because of the threat of multi-drug resistance. So that's a huge disincentive for a pharma, right? Because they're saying, well, why would we develop something at such a high price tag to have it sit there on the shelf? And obviously, with multi-drug resistance emerging so quickly, the shelf life of an antibiotic doesn't last as long as it did before. So, and that's another area where phage can actually improve the situation, because phage can be used as a direct, lytic drug, but here the drug is alive. But it can also be used with antibiotics to put selective pressure on the bacterium so that the bacterium has to make a genetic decision, if you will. I'm using these anthropomorphic terms just to kind of
Mhm.
drive the point home. But so in my husband's case, when we used phage with an antibiotic, It was two phages and a phage cocktail along with an antibiotic minocycline. And he had actually been resistant. This bacterium had been resistant to minocycline, but those two phages had a synergy with the
Hmm.
antibiotic that was just turned out to be opportunistic. And so what happened was the bacterium dropped its capsule in response to this double threat. And the capsule was where the receptor was for the phage. So the phage were no longer effective, but in dropping its capsule, it became like that less virulent, and it was easier for the antibiotic to work to kill it. So it was a real 1-2 punch. So I'm kind of getting ahead of myself because that
Hmm.
was the final chapter in my husband's cure. But it's one that makes the pharmaceutical industry excited because it's not like phage is ever going to replace antibiotics. And in fact, if phage can make antibiotics that have been sitting on the shelf work again when they weren't working before, then that in itself is a game changer for the field.
Well, let's talk about phages because, um, there was a moment in the history of the germ theory where every bacteria was considered, bad, and I think we've come back to a more balanced perspective where we understand that there's this thing called the biome, and on the human body we need all these bacteria to help us thrive. We have a symbiotic relationship with all of these bacteria, but viruses particularly today kind of get a bad press, right? I mean, there's no the only good virus is a dead virus, right? I mean, I think that's what a lot of people think. But you talk about the virome, and this seems to be an area of research that is kind of only in its infancy, right? I mean, you mentioned that each person is carrying around trillions of viral particles, right, that are reproducing, in the body. um, so, why is this area of research so? I mean, we're starting to think more carefully about downstream consequences of different viruses, right? People are talking about how things like Epstein-Barr may have, long-term consequences on the brain and so forth. But very few people are talking about kind of the positive impact of viruses. And sort of as an economist and a lawyer, I'm trained to always think about the opposite side of every argument. So I remember when I first learned about phages 20 years ago, I was like, now this is fascinating, right? What's the state of the art right now, just in terms of thinking about the virome? I mean, are we at the only beginning stages of this notion that viruses are both good and bad?
Well, it's interesting because when people talk about the microbiome, they're generally focused on the bacteria. And they don't realize that phage, which are the natural predators of bacteria, they're viruses that have naturally evolved to attack bacteria. That it's the phage that are the gatekeepers. They help with the turnover. I mean, if there was no phage in our bodies, then we would be overrun with bacteria. And in fact, phage also keep the numbers of bacteria in the oceans in check, and so they're everywhere. They're thought to be the oldest, most populous organism on the planet. They have been co-evolving with bacteria for almost 4 billion years. And it's thought that there's a nonillion of phages, so that's 10 to the power of
Mm.
31. So 10 million trillion phages on the planet. So the problem is that we haven't really known how to measure or culture many of them. Microbial ecology is now, spending a lot of time, characterizing phages and identifying phages through techniques like metagenomics, which are fairly recent. So that means that people can actually splice together pieces of DNA and assemble a virus. In fact, phage, which is one of the most populous phages is in our guts, was actually discovered through cross assembly, which is where the name came from, which was the first time that metagenomics had been used to identify a phage. So those techniques are relatively recent, And it's one of the reasons why phage have been considered the viral dark matter of our
Mhm.
microbiomes. And even though phage have been used to study life processes and molecular biology and recombinant engineering and cancer, tech therapies and things like that, um, they really have lost science lost the application of phages for therapy, except for the very important role that the former Soviet Union, especially the Republic of Georgia and Poland, have played in this story, and that actually, is another tangent that we address in the book as well. That because phage were discovered before antibiotics. So phage were discovered in 1917 by Félix Dejarel, a self-taught French-Canadian microbiologist. And he was a pretty egotistical guy. He ticked off a lot of Nobel laureates and insisted that what he found must be a virus that was parasitizing bacteria. And they didn't believe it. They thought that it was probably an enzyme, and there was a big debate about this. But nevertheless, Félix went on to use phage to successfully treat bacterial infections in humans and people. And he was the inspiration for the protagonist in the book Aerosmith that won the Pulitzer Prize, right? And so this is obviously way back before World War II, but World War II played an important role in this because when phage were taken up by what is the former Soviet Union, it was part of the socialized medicine view that Stalin embraced. And he apparently blessed a cottage called Dejarel's Cottage on the shores of the Tbilisi River. And so that gave this whole field a really bad
Mm.
reputation, right? Because this is enemies, Soviet commie science, that kind of thing. So Bill Summers, who's a historian, a medical historian, has done wonderful research on Félix Dejarel's biography and really chronicled how researchers viewed Dejarel and also phage through this lens of World War II. And in fact, a famous father of molecular biology, Gunther Stent, who's from UC Berkeley, in the 1960s, he published a monograph where the language that he uses is clearly very biased against Dejarel and against these out of the way places where this
Mhm.
poor science is being done. And that was considered to be the death knell for phage therapy in the West. So it was really forgotten until fairly recently.
Well, I mean that's a fascinating intellectual history. I want to hear more about it. You in the book you quote a letter that you wrote or an email that you wrote when you first started thinking about doing research into phage therapy for your husband's treatment, and you said, "Hey, this might be a little woo woo." I remember reading that and I was thinking, "Wait, why?" I mean, okay, look, if you're talking about crystal therapy, if you're talking about, astrology or something, maybe the woo-woo might be the appropriate descriptor, but, why were you initially a little bit, I don't know, uncomfortable with this? I mean, why did this have I mean, I understand the Russian taint from kind of the Cold War, but why circa, the 21st century was this area of research considered even, potentially woo-woo among medical practitioners?
Well, it really got the reputation for a while of being fringe science. And certainly some of the early research that was done on phage therapy was inferior because at the time we didn't even know that DNA had a triple helix. And
Mhm.
Felix was, experimenting on himself, his family members, his lab members. I mean, that was kind of commonplace. But, and certainly there were also people that were trying to, estrange him from the field, and he was, there was lawsuits and also a couple of early companies that tried to commercialize phage preparations really overpromised and
Mhm.
underdelivered. It wasn't really known at the time that phages are very specific, and a certain phage only matches onto a certain bacteria, say, an Acinetobacter baumannii. My husband's bacterium, it actually is the phage are so specific they have to match to that specific isolate, not just the genus and the
Mhm.
species. Other phage we know now, say phage that's active against staph, are less finicky, if you will. Say 20 to 30 phages may cover the vast majority of circulating isolates around the world. But Felix believed back in the 1920s and 30s that there could be a universal phage. And also, the companies like there was, I think, one of
Well, I
them
mean, would we
became
want a universal phage? I mean, that would presumably attack all the good bacteria as well as the bad, right?
well, in fact, there's research being done to develop synthetic phage to do just that. But at the time, like nature didn't produce a phage like that for us that anyone has found. The host tropism of phage is relatively narrow, and that's part of the benefit in some cases because you don't want to have an organism that kills all the bacterium in the microbiome, right? We know that bacteria have a friendly, important role. And so you only want to selectively remove the pathogenic
Mhm.
bacteria. Anyway, it's really fascinating to consider that some of this early research was ahead of its time, but because there were some Achilles heels, and one of the companies was treating the phage preparation to make it more stable. And in doing so, it inactivated it. They didn't realize
Mm.
that. And they also said that phage could be used to kill viral infections when it was only, going to be able to kill bacterial infections. So all of those things gave it a reputation of being not up to par. And perhaps even the pharmaceutical industry, encouraged that and because phage therapy has been continued to be used in the Republic of Georgia and in Poland, and forgotten in the West, there's still a bias to this day, especially older physicians, infectious disease physicians who learned in medical school that this is like
Mhm.
enemy science. It's foreign. And it's not. The research hasn't really been done. And it's true that the clinical trials that really should have been done back in the day haven't been done yet, and they're just getting started now.
Now, you're a PhD, but not an MD. Do you think that being a PhD maybe made you a bit more open-minded about these alternative approaches? I mean, you started as you said you abandoned your career as a microbiologist relatively early on, but is the medical community sort of more prone to kind of sticking with the tried and true, sticking with the routines and the protocols, right? Um, and kind of less open to alternatives. I mean, do you credit your kind of status as a PhD and not an MD as maybe contributing to your open mindedness around these new therapies?
Well, I've met a number of MDs who are very open-minded, and certainly Dr. Schooley, Dr. Robert Schooley, who's known as Chip, he oversaw the protocol for phage therapy in my husband's case. And when I presented him with this idea of using phage therapy to save his life, he actually, said, "What an interesting and intriguing idea! If you can find phage that will match his isolate, I'll call the FDA and get permission." So certainly, he's like-minded, but I can tell you we have run into a number of infectious disease physicians who have been reticent to use phage therapy. In the US, we certainly have, a litigiousness that has made people very risk averse. In my husband's case, there was a very long consent form, and we had to get lawyers involved so that they were assured that if he died, that I wasn't going to sue anybody and that kind of thing. That's more of a US phenomenon, I have to say, but, in the UK, a very famous, lung transplant physician who was asked to provide phage therapy for a patient who was dying called phage therapy voodoo.
Mhm.
That was fairly recently. So we have a long way to kind of overcome this feeling that it's fringe. But with the more science that's getting done by reputable researchers in peer-reviewed journals. A mesh term for phage therapy was created in 2017, and since then, there's been like literally thousands of papers that have been written, and many of them published in Science, Nature, top journals. So it's certainly seen as the most promising alternative to antibiotics that's out there right now, and the NIH has invested $12 million in a trial that is going to be conducted through the Antimicrobial Resistance Leadership Group, which is a network of research institutions around the US that has been investigating new antimicrobials. And, up until recently, that was just, small molecules like antibiotics. But now they've embraced phage. And so this trial just started recruiting participants. And we're going to need many trials like this for different kinds of conditions and different types of bacterial infections to be able to convince the FDA that this is something that could be licensed alongside antibiotics. But right now, it's just they approve compassionate use cases on a case by case basis.
So, kind of the slowness to kind of invest in this research, is it? I mean, it doesn't seem like a conceptual problem, right? I mean, antibiotics are their whole, you know, modus operandi is to essentially manage the ecosystem within the body, right? I mean, penicillin is a fungus, right? So we unleash a fungus on a bacteria. So unleashing a virus on a bacteria doesn't seem that conceptually different from what we're doing with antibiotics. So is the kind of main psychological or practical obstacle to pursuit of this research really about the execution? I mean, it doesn't seem to be a conceptual problem. It's really more a practical one, right? It's just these are finicky, they're difficult to identify, they're difficult to match, right? And so resources are needed in order to make sure that these can be kind of unleashed effectively, right?
Yeah, but the obstacles that exist are surmountable, but I can certainly explain to you where they are right now. So first, if someone has a bacterial infection that is not responding to antibiotics, and we, think that the FDA would give approval if we had a phage therapy program set up for this person, then we have to find those phage. And even though there's 10 million trillion phages on the planet, you've got to find the perfect predator, if you will, to kill the
Mhm.
bacteria that you want to knock out. And sometimes that's easy because, the host tropism of the phage is broader, like I said with staph, and other times it's much narrower, like with Acinetobacter baumannii. And some phage labs at research institutions and even phage companies have libraries of phage that are already
Mhm.
characterized from the environment. And when I say the environment, I'm talking environment, like because where you source a lot of these phage are some of the gnarliest places you can imagine, right? Because wherever you find a lot of bacteria, you find a lot of phage. So a great place to go to find them is sewage and barnyard waste and duck ponds. I mean, literally, my husband's phage were sourced from shit and the
Yeah, well,
bilges of ships.
that to me was interesting because I would have thought that if you were looking for the perfect predator for the bacteria that your husband had, you would go to Egypt, you would go to Iraq, right? You'd presume that that would be where they live. If you're trying to find,
Well,
a
yeah,
predator
I
for
mean,
antelopes, you go to where the antelopes are. But you found this in sewage outside of, Baltimore, right? Like is how did I mean, if you're trying to match the predator to the prey, is there some kind of ecosystem approach that you could use to make that search
well,
easier?
yes, I mean, you're hitting upon some really important questions. So, for example, Dr. Ry Young, who turned his lab into a command center to search for phage for my husband Tom, the first thing he asked was, "Do you have any dirt on the bottoms of your
Yeah.
shoes that when you came back from Egypt that we could look for phage?" And of course, we didn't. So he said, "Okay, well, we'll look in our phage libraries, but also put a call out to researchers around the globe and." you know, um, Finding phage in Maryland to match a bacterium that got picked up in Egypt, it just shows you like we're in a globalized world here. I mean, somebody was probably in the hospital at the NIH, and some of the gnarliest superbugs that you could
Mhm.
find are in the sewer system, associated with that hospital. So, and the Navy, the U.S. Navy got involved, and they had found their phages in the bilges of ships from all over the world. So anyway, that's what happened in my husband's story. But basically, there is no centralized giant phage library that exists in any one place. There's lots of little libraries. So it's like, having a million keys and you've got to find a
Mhm.
million, parse through a million locks to find the right key that matches to the lock. So what we really need to do is build a phage library that maps onto a superbug library. And of course, these are going to be constantly needing to be updated because these are organisms that are co-evolving to attack one another. But it really is not expensive to source phages. In fact, and it's not hard. In fact, even high school students and college freshmen learn how to isolate phages from sewage samples in a program called the Phages program that operates out at the University of Pittsburgh. And they have a phage library of over 15,000 phages that are generally only active against one family of phages of bacteria, mycobacteria. But interestingly, after my husband's case, it was publicized, and we had this deluge of requests from all over the world. One of those requests was from a young girl in the UK who was dying from a superbug infection following a double lung transplant that was associated with her cystic fibrosis. That's actually a very common situation for these patients. So she had a Mycobacterium abscessus infection, which is a cousin to tuberculosis, the biggest bacterial killer in the world. And that's the family of phages that the Phages program has in their library. So we approached them and said, do you think if you could see if any of these phages would be a match for her infection? And they found one that was a wonderful killing machine. And they found two others that were not the kind of ideal phage that you want for phage therapy. Those are called temperate phages. They enter the bacterial cell, and instead of turning it into a phage manufacturing plant, in the phage rage kind, those phage integrate into the bacterial cell DNA and hit the snooze button. So you don't want to use those phage. They can carry antimicrobial resistance genes or toxin genes. But if that's all you can find and you want to have more than one phage, ideally in a cocktail, so that in a perfect world, they'd be hitting different receptors so that it's harder for the bacteria to develop resistance against both. So you want this phage cocktail, but if you can't find a perfect phage, then you have to genetically manipulate the DNA, and that's what they did. So this became the first genetically modified phage cocktail to successfully be used to treat a human mycobacterial infection. And Isabel, the patient, lived another 3.5 years. She unfortunately died earlier this year, but it certainly wasn't from a lack of phage. She, made a complete recovery, even though she had been in hospice, as complete as you can, given that she had cystic fibrosis. She learned to drive. She had a part-time job. We would send each other silly cat memes through Facebook Messenger all the time. So I just tell you this story because a phage library allows you to source phages a lot faster. If those phages are already characterized and sequenced, and you know what other phages they go best with, and you know what receptor they hit, that's great. So that's what we need. And angel investors out there that are interested in getting involved, that's certainly one of our areas of need. We also need GMP facilities, so good manufacturing practices, like with a bioreactor, so that you can make clinical grade phage, because research labs at universities are not set up for doing that. They might be able to say, okay, we found some phage, but then if you've got to purify and expand it and characterize it, someone else often needs to do that. So, and then the last thing that you hit on is, well, couldn't we be clever about microbial ecology and say, if this is the kind of bacteria you have, where do we go to find phages that are going to attack it? We don't know that. In most cases, we don't know, because we don't know enough about, the environment that these phages and the bacteria live in. I can tell you that there are some interesting examples. So, an organism called Burkholderia, in fact, Burkholderia cepacia, which is common in CF patients with lung infections, it's commonly found in rice paddies in Southeast Asia. So, and these things are kind of discovered kind of accidentally, but if we got machine learning techniques to be clever about where to source phage from, we could be a lot more efficient, because, I take skunk poop from my backyard down to our lab, and, my colleagues say, okay, well, maybe we'll find some E. coli phages. But If they didn't, it doesn't say mean that there wasn't phage for a totally different
Yeah.
bacterial infection there, right? So anyway, we need a lot more research in this area, and phage therapy is undergoing a renaissance, but so is microbial ecology.
So we can imagine a world where, someone has an infection. You culture the bacteria, you identify the characteristics of the bacteria, and then you have this phage library, and then you can either try out a bunch of different phages, which is what happened with your husband's case, to see which ones work. Or if you know enough about the characteristics of the phages, you might be able to just identify purely based on the data which one's going to work, and then you target them. And this would be kind of like a precision medicine approach. But I guess one question I have is, like, why don't we do that with antibiotics? I mean, you talk about how as soon as your husband got sick, you gave him a Cipro. I mean, a Cipro is a broad spectrum antibiotic which just kind of kills everything in its path. But antibiotics also are more effective and less effective on certain things. Why don't we have? I mean, what are the institutional obstacles to having some kind of more precision based approach with antibiotics? And if that is impractical, why would it be practical to do this with phages?
Well, you raised some really important issues here because what's really lacking is point of care diagnostics. When someone presents to a hospital or their physician with a sore throat, when he looks at their throat and sees some white spots on it and goes, "Oh, it's probably strep, so I'll give this guy antibiotics." He's guessing, right? And it might be a good guess, it might not. It might be a viral infection instead, in which case it would be inappropriate to prescribe antibiotics. What's lacking is a way to do an antibiotic susceptibility profile right on the spot, and that's called an antibiogram. It was done in my husband's case in Germany once he got medevac from Egypt to Germany. But like many hospitals, it takes several days to get that back. It's not usually something that they can do in house. And certainly in lower and middle income countries, they don't have that capability whatsoever. So as a result of that problem, there's a time delay, and the patient needs help, or the physician wants to feel like they're doing something. The patient wants to feel like the physician's doing something. So it's guesswork. There are techniques that are being developed to be able to develop point of care diagnostics, but they're expensive, and so they're not readily available in most hospitals. So we need to solve that. In terms of phage, I can imagine a situation in the future, though, where because we have sequencers that are portable and cheaper than ever before, that you'd be able to sequence a phage and sequence a bacteria and be able to have a database to say, okay, this phage will match that bacterium, or to even genetically modify or synthesize a phage. So in a kind of like a 3D printing kind of model. And some of my colleagues in Belgium have, been working on that. So I think that there's going to be advances that are going to help us make this work. But right now, we need phage libraries. We need more investment in clinical trials. If we made, 5 COVID vaccines in a year, the political will and the resources can be there. But right now, antimicrobial resistance isn't on the radar of most people. And that's one of the reasons that we wrote our book, The Perfect Predator, because if I was blindsided by the superbug crisis, then the average person probably isn't aware of it either. And we were so privileged, really. I mean, oh, yes, it was the worst thing that could ever happen. My husband was in the hospital for 9 months. He had 7 cases of septic shock, but he was saved by science. And, yeah, little me and some doctors and researchers, a global village of people that stepped up to save his life. And so when you started this, you said that the book is about, the discovery process. And I think that that's what I went through at an individual level, but it's because your back is up against the wall, right? That's the moment where you think outside the box. And in fact, that's when penicillin came on the scene in, World War II, because people were dying on the battlefield of bacterial infections that could be treated with penicillin. So I think that, when your back is up against the wall, whether it's you as an individual or us as a society or a planet, It's when we, can sometimes have creative ideas to come up with solutions that we wouldn't otherwise do. And that's what I'm hoping that we'll do now, because both climate change and antimicrobial resistance are colliding. There are two problems that are making each other worse. And in our lifetime, we're going to see people dying from infections that used to be treatable. And I get those phone calls from patients every day now. A guy who steps on a nail, and now that infection went into his bloodstream or his bone, and he's going to lose his leg. It's like, what? It's a
Hmm.
silly E. coli infection. Like, what? So, imagine going into the hospital to get a prosthetic knee or hip, or to get your pacemaker line swapped out, and you get a superbug and there's nothing to treat it. I mean, we're really at that point now. So I'm not being histrionic. As a result of my husband's case, I now get approached by physicians and patients and families from all over the world. And that's why we opened our center, the Center for Innovative Phage Applications and Therapeutics. It's a nonprofit based at University of California, San Diego. And I'm happy to say that Baylor, Yale, and the Mayo Clinic all have phage therapy programs as well. The UK is just about to launch their nationwide phage therapy program through the National Health Service. Canada just treated its first patient. There's a Phage Australia. There's a phage therapy program in Belgium and France. There's a new one in Sweden. And of course, the Georgians and the Poles have been doing this for
Hmm.
decades, and they're going, it's about time, people.
Hmm. Well, so now you mentioned primarily the use of phages as therapy after people are infected, after they have kind of run out of other options. But could you imagine a day where phages would be used sort of preventatively? I mean, in the book, you weren't clear. You don't know whether your husband caught this. When I was reading the book, I thought you were going to say that he got it, going into that pyramid, right, where the with the bad air is like, oh, don't go down there, right? But then later you say it was probably from the nasal tube that he received in the hospital in Egypt. I mean, would it make sense for us to think about developing antiseptics that are phage based, so you could just unleash these on all of the tubes and all of the equipment that's all throughout the hospital to kind of tame the population of these superbugs? Because if we get to a stage where going to the hospital is a death sentence, then people aren't going to go in for treatment. They're not going to go in for. I mean, I know people that are actually afraid of going in for surgery because of MRSA and other kind of superbugs.
Yeah. Well, I like the way you think, because certainly right now we've been talking about phage for therapeutic reasons when someone has a bacterial infection that's not responding to antibiotics. But there's phage that are being used as prophylaxis. It's, again, that's research. So in the case of a very contagious, serious bacterial infection like cholera, if one person in a household gets
Mhm.
cholera, almost everybody does. So you could potentially use phage to treat those other family members, so that
Or
they don't get
drop it
cholera.
into the, if in, there's open sewage, you could drop it into the open sewage to kind of neutralize it in the.
There's work being done using phage for surveillance of sewage, but also potentially treatment. There's phage that's being examined to actually take away the slimy layers that clog pipes in the middle of the ocean. There's phage research being done to replace or reduce the amount of antibiotics used in livestock and in farming. And there's also phage being studied to groom the microbiome, to take out the unfriendly bacteria and to promote wellness as sort of like a probiotic. And because we were talking about precision medicine, this is exactly that. This is kind of like where nanotechnology meets precision medicine and phage therapy, because phage, we know from my husband's case, we injected 1 billion phages per dose every 2 hours initially, and he did not die of septic shock. And we haven't seen untoward safety issues with phage therapy. So what that means is that you could program phages to be little nano shuttles, and there's companies that are working on this. So they're using CRISPR-Cas gene editing to program these phages to attack tumors, to carry, vaccines, all of that. So it's a very exciting field of nanomedicine, and I'm happy to watch it kind of flourish. It's really weird to think that, you know, your husband and you go on vacation, And, he looks healthy and something goes sideways, and then all of a sudden he's dying, and then all of a sudden he has this miraculous cure, and now that cure is being used to help other people. I mean, it's, uh it's been described as kind of the watershed moment in the strange history of phage therapy that brought it back to the West. And those aren't my words, but it's an honor and it kind of fuels us because, it changed our whole lives. And my husband had, 5 years of recovery from all of this. For every month
Mhm.
that you're lying in a hospital, it takes 5 months to recover. So, and it's just so gratifying to see that something that could be initially so terrible could end up having a silver lining that's helping other people. We're really blessed.
Mhm. Now, when that light bulb moment happened to you, when you first kind of discovered kind of phage therapy or began to seriously consider it, did you at that moment ask yourself, you know, wow, why didn't I notice this 6 months earlier? Or was there was there kind of a realization that um, this thing was out there all along, kind of waiting to be discovered by you?
Yeah, in the book, I kind of make a passing joke at my obsession with forensic files, where
Yeah,
the answers are right there. It's just they can't see them, and so
right.
I kind of felt like there's got to be something that exists that we can do to find something that will knock it. Because I took this really personally, right? I'm an infectious disease person, and my husband's dying of a wimpy bacterium that I used to plate on my petri dishes back in 1986. Like what? So, and when I stumbled across phage therapy in the literature, and ironically, a girlfriend of mine from San Francisco, from UCSF, emailed me and said that a friend of hers had gone to Tbilisi, Georgia, to get her MRSA treated with phage
Mm,
therapy. And so I just thought, wow, it's kind of almost like the planets are aligning here. And so that's when I thought, well, maybe there's something to this, and I dug deeper into the literature and then approached Chip, and he said, yeah, let's see if we can make this work. But, yes, if we had found phage therapy, much earlier in the course of Tom's infection and gotten it, he could have walked out of the hospital within, a short period of time instead of like it taking months because he was so deconditioned, lost 100 pounds, was on a ventilator for months, it was in a coma, you know. But let's face it, the FDA would never have approved
mm,
it unless he was dying and it was a last resort. So we had to, as they tell me, we had to have a Tom Patterson. We had to have a
yeah.
patient who was dying, a family members that were willing to try it, a hospital that was saying, okay, well, we will cut through the red tape to make this work because we're a teaching hospital and we embrace experimental cutting edge treatments. Other hospitals and universities might not have done this. I've been told by many of my colleagues that their university would never have done this. And that's because the patient was about to die. If it was, he was just sitting there going, "Oh, I don't feel so good. I don't want to take antibiotics. Can we do this phage thing?" I mean, we have patients contacting us now who don't want to take antibiotics any longer. They have some side effects or whatever, but their organism is still susceptible to that or other
Mhm.
antibiotics. And the FDA says, sorry, like, it's not indicated for that right now. We have to do the trials. So that's where we're at. We've treated dozens of patients at IPATH, but there's like several hundred patients around the world that have been successfully treated with phage therapy as a result of my husband's case. We don't always have successes because we don't always get the phages in time, and that's why we need a phage library and really a consortium of partners that are willing to work on this. And we're looking to develop a private public partnership to bring this to scale because it's not scalable the way we're doing it right now. It's kind of each time it's this very long, arduous process, and it makes me realize how lucky we were to have all the planets line up for Tom. He's sitting here just have coming back from his 3 mile walk, and he's just made me lunch. So I'm feeling pretty good about life right now.
Well, I mean, look, you and your husband both were veterans of the kind of HIV battles in the 1980s and 90s, and it was a big struggle to get these novel therapeutics into practical use, and there was the FDA is, and I think justifiably um, adhering to the kind of precautionary principle, right? They're very reluctant to allow experimentation with novel therapeutics. Do you think that there needs to be a different approach? I mean, do you think that they need to be a little bit more open to experimentation? I mean, do we essentially overweight the problem of kind of false positives and kind of underweight the benefits of experimentation in general?
Well, I think you're talking about a couple things. First, I'd say that through the HIV epidemic, creating a pathway for compassionate use treatment of experimental therapies is what happened while the clinical trials were being done. And that was in advance. And certainly, my husband benefited from that compassionate use program that the FDA has. There has been a movement for this right to try that has in recent years to try to almost abscond with the FDA and to allow people to use experimental treatments willy-nilly. Well, I'm certainly not a proponent of that because we do need data, and even in an N of one case like my husband's, we collected valuable data that we published, including the protocol to treat him that moved the field forward. So certainly, that not all parts of the FDA work exceedingly well at the same time. But I can tell you the office that was handling fecal transplants that is now handling phage therapy requests has been fantastic. They are giving us advice on how to develop standardized protocols that could be used so that approvals happen faster. We haven't been turned down for a single request from them, so they want to see this succeed. They see that this is a huge problem. AMR is getting worse and not better, and that phage could be a really important quiver in our arsenal here. And it certainly won't ever replace antibiotics, but I think if it allows us to use antibiotics more judiciously and more in a more clever way, then we'll be able to get ahead of this superbug crisis.
Well, I want to end with two questions, and they're I think they're unrelated. But the first one is, you watched in real time how evolution was working on your husband's bacteria, right? I mean, you'd apply the phages, and the phages would sort of stop working after a while, right? I mean, this is evolution in real time. So, first question is, do you think that doctors and researchers kind of need to think of themselves as sort of evolutionary managers to some degree, right? Where they're orchestrating an ecosystem. And then I guess the second question is, you mentioned the importance of intuition. You talk a bit about how your gut was kind of telling you that you needed to kind of pursue this line of inquiry. um and there's a big debate over whether practitioners and researchers should kind of listen to their gut. Of course, you need to do data, and you have to have strong research behind it. But in terms of deciding where to focus your efforts and where to pursue inquiry, um, how do you need to have a good gut? Right? Do you attribute your do you have something special in your gut that would lead you to kind of ask the right questions?
Well, I think the second question is easier to answer first. I think I don't know if it's your gut so much as your subconscious, perhaps, or just being open-minded. And I think that you really need to be able to grasp ideas from different places sometimes. And there are other scientists that look at, different patterns in nature and that they've taken that as inspiration. So, the strength of a spider web or the stickiness of a gecko's pads on their feet and things like that. So, and those kinds of things have inspired some really amazing innovations. But in terms of, watching evolution, so to speak, during treatment, well, in this case, it really is happening because the drug is alive and the bacteria and the phage are co-evolving within the patient. So what we really need is pharmacokinetic and pharmacodynamic studies to figure out, okay, if you give this amount of phage to somebody, how much is the phage is the patient actually getting? Because the phage are going to be multiplying as long as they find bacteria that are a target. So those studies need to get done. But even in something like cancer, tumor cells are evolving to, become resistant to different, therapeutics that are being used. So it's all about being able to take the data at a micro and a macro level and looking at the patient. I mean, I'm not a doctor, but Chip taught me. He said, "Look, yes, the phage have become, useless because the bacteria got resistant. Well, we didn't know when we gave him these phage cocktails that we were using essentially the same phage. It was like there were, a couple of nucleotide bases differences, and we didn't have them sequenced ahead of time to know that." But he said, "Look at the patient. The patient is getting better. We've knocked down enough bacterial burden that his own immune system is kicking in and is able to fight it now, whereas it wasn't before." So there's something to be said for that. And our book has actually been used, in medical schools as well as, microbiology and epidemiology classes to teach some lessons. My husband said that he could hear while he was in a coma. I mean, that was a big shock to grand rounds when we gave it at UCSD. It's like, oh my God, people were saying things to me like Father Confessor. So there's lots of different lessons to be learned from this story. And my husband and I are obviously just so grateful that we had this experience, and we've had at least 6 more years of life together. And what better way, to live your life, realizing that there's a kind in the word humankind, that total strangers can step up to the plate to save somebody's life. And if we can do that for one man, we can do it for the planet.
Mhm. Well, Stefanie, thank you so much for joining me. The book is The Perfect Predator, and it's a case study, but it's also, I think, a um, provocative study of kind of, I don't know, research evolution, and has all sorts of interesting suggestions about how we can dig deeper into this new type of therapy. Thanks so much.
Thanks very much.
This is Unsiloed, brought to you by Alumni FM, connecting people through stories.